Okay, geometry. I'm homesick with a kiddo, and I'm kind of fighting off something a little bit too, I think. So hopefully my coughing doesn't disrupt this video too much. I'm going to go over notes for section 2.5. You do not have these notes yet, so I don't know if you guys are in the library or if you are in my classroom with a sub. So I need somebody in the group or a couple people in the group to go into my room and get the notes for section 2.5. And there's a homework assignment. It's a handout. Um, for this section as well, and go ahead and pass those out to everybody so that you can finish watching this video. So go ahead and pause the video now so that you can get those notes. Somebody do that for the group or whatever, and make sure you get those from my front table in my room. Okay. All right, so after you have those notes, I'm going to go ahead and just go through these. We only have two examples, but they're both proofs. But they're both not hard. They're not terrible. We do have a bunch of postulates going on, and normally we would write these down in our on our purple sheet, but I don't have my purple sheet with me, and so we're just going to wait, and I'll write those down with you on Tuesday, tomorrow, when I come back. So we'll wait to write those down until I'm there with you. So in section 2.5, so postulate 2.8, I will go over these even though we're not writing them down. So postulate 2.8, if you can kind of remember from section 2.4 when we first introduced it, like postulates and theorems. Postulates are like the basic concepts, like the, oh yeah, that just makes sense concepts. Theorems, though, are kind of like the big brothers to the postulates. They're the big guns. They're the ones that actually take a little bit of thought process. And really a theorem is basically a proof or has been proven from a set of postulates. So that takes a couple postulates together to prove something, and then that's called a theorem. So both of them you can use to prove other things, but theorems are like the big brothers. So postulate 2.8. This one is super silly. So in words, it says the points on any line on a segment can be put into a one-to-one correspondence with real numbers. What that means is if I have a line segment like AB, I can measure it with a ruler. That's basically what the ruler postulate says, okay? Sometimes postulates are really kind of almost redundant. They're like stupid. Yes, of course you can measure a line segment with a ruler, whatever. So that's what postulate 2.8 says. Now, postulate 2.9 is a little bit more in depth. And we have talked about this before. This one has a special name, and we will talk about his special name. We'll make sure and write that down on your purple sheet, but it is the segment addition postulate. We'll use his name a lot. And so basically what the segment addition postulate says is that if I have a line segment AC and B is somewhere in the middle, not necessarily exactly in the middle, but he's somewhere between A and C, if I take the length from A to B and I add it to BC, that should make up the length of AC, right? If I put numbers to that, and let's say AB has a length of 10 and BC has a length of 3, then AC is going to have a length of 13, right? AB, this length right here, plus BC is going to be the entire length of AC. That's just what the segment addition postulate says. So this is the really important part. AB plus BC equals AC. If I have those two parts individually, I can add them together to make up the entire thing, okay? So we have a proof to start out with that has to do with that segment addition postulate. Okay, so they say, prove that if, and I'm going to mark on my diagram over here as we go through this information, prove that if CE and FE are congruent, that's what this symbol says. This guy means congruent, which means the same shape, same size. So if CE and FE are the same, CE is this length right here, and FE is this length right here. I'm going to put a little tick mark on each one to note that those are the same. And ED is congruent to EG. So ED is this bottom part right here, and EG is this top guy right here. I'm going to use a different color. And I'm also going to use two tick marks. So I'll show that this guy is the same length as this guy. So what we're trying to prove then is if this piece matches that one and this piece matches that one, then the length of the entire thing, CD, has to match the length of the entire FG over here, okay? Which should just make sense, right? But we can't just say it is because I said so, right? So we have to prove this. We have to prove why that's true. Okay, so I'm going to walk you through this one. We are given the fact that CE, I'm going to write it exactly like they do from up above here, CD, so is that CE? CE is congruent to FE, and we're also given, I'm going to put comma, ED is congruent to EG. EG, okay? We're given those two things. That's this part right here and this part right here. And then what we're trying to prove is that CD is congruent to FG. Okay, those are the things that we're given this, we're trying to prove that. And here's my proof, and I'm going to do 2-column proof, so I have statements and reasons. It's already ready to go for you. Okay, so I'll try to write small if I can, because this pen is kind of fat. So we always start out with what we're given. Always, always, always. If you don't know how to start a proof, you should at least have the given down. Okay, CE is congruent to FE. Okay, and I'm going to put ED is congruent to EG. Those two things are true, okay? And that is given to me, okay? All right, so I'm going to put a line underneath of that so I can go to my next statement here. So that's given, all right? Now, the next thing that we're going to talk about, the next thing that we're going to do is something weird, which really just takes this, and instead of saying congruent, we're going to say equal. Okay, so we're going to say that CE is equal to FE, and ED is equal to EG. Okay, so rather than saying that they are congruent to each other, same shape, same size, we are saying by saying that they're equal, we're saying that CE, the measure of it, is exactly the same length as what this guy is, okay? And ED is exactly the same length as EG, okay? So that's just one weird step, and you'll see that going forward probably a whole lot, but that is called the definition of congruence, C-O-N-G-R-U-E-N-C-E, definition of congruence. Now, if you want to be lazy, you can write the symbol for congruent. That's totally fine. Definition of congruence. So basically takes that and makes it so that they are exactly equal to each other. They are exactly equal. Okay, so there's that thing. All right, now I want to talk about CD for just a second. Okay, CD, the entire length of CD from the segment addition postulate, CD is made up of two pieces, right? This whole length is made up of CE and ED, right? Okay, so CD is equal to CE plus ED, okay? Now at the same time, I'm going to write out what FG looks like. Okay, so you might be able to figure this one out already. FG is this guy right here. Excuse me. FG is that whole thing right there. And he is made up of FE plus EG, right? And how do I know that that's true? Because of the segment addition postulate. Okay, we will use him so often that we will most of the time use his name. If you want to put postulate 2(9), that's not wrong, but we will most of the time refer to him as the segment addition postulate. So I'm gonna call him that instead. Okay, so there's that guy. All right, only a couple more things. This is a little bit longer of a proof, but we have just a couple left. So I'm writing really fat, so hopefully you've written a little bit smaller and are not having to extend your page, because you can extend your page. That kind of stinks. So I'm gonna extend mine down because this marker is really fat. Okay, now a couple more things. So if we have CD is equal to CE plus ED, and FG is equal to FE plus EG, then why don't we do this? Why don't we try to make this part right here, we're going to make him look exactly the same as this part right here, okay? Then we can maybe say that CD and FG are the same as each other. So if I can make this part right here look exactly the same as this part, then I can call these two the same. So CE and ED. I know that CE and FE are exactly the same. So instead of saying CE, I'm going to put FE in its spot, okay? So I'm going to say that CD is equal to not CE, but FE plus ED, right? I'm going to make him look like that, okay? So CD is CE is going to change to FE because that's what they're equal to, right? This guy and this guy are the same. They're interchangeable, plus ED, okay? But then I can say, well, FG, if I want to make him look the same as this, I already have the FE part, but isn't EG the same thing as ED? Right? Those two are interchangeable from one another. So I can, instead of this guy, I can replace him with ED, right? So ED, right? So I have CD is FE plus ED, and FG is FE plus ED. So basically, they're both kind of the same thing, right? And then I can go down here further, and I can say, well, hey, since they're equal to the same thing, then they're equal to each other, right? CD is equal to FG, right? Okay, so that's the next step down here, but we need to decide what we did here. Like, what did I do, or how do I know? What's my reasoning for being able to plop in FE here and plop in ED here, right? And what that basically is just basic substitution. That's the substitution property. That's what we talked about in section 2.4. Okay, substitution property. Okay, now this one, CD and FG, that's substitution as well, because I have taken FG and plopped it in for this big junk right here, because that's what FG is equal to. FG goes in this spot, and then I have CD equals FG, so that's another substitution property. Substitution property. Okay, now the last thing that I need to do, I don't want CD equals to FG, I want CD congruent to FG. Okay, and so that's kind of the reverse of what we did up here. If CD equals FG, then I can say CD is congruent to FG, and that is the definition of congruent. And I'm going to use this symbol now. This time. So definition of congruent is what basically took him from congruent to equals. It also takes him from equals back to congruent. Okay, so this is not just saying they're equal in measure, but they're exactly the same is what congruent means. Okay, so then that's done. I have my proof done, and I write my symbol, and there we go. Okay, so that was a little bit longer of a proof, and it's not hard to follow. It's not hard to see each one of those steps. Maybe hard to generate by yourself. But I think what they do for this homework assignment is they give you basically the skeleton of the proof, and they have you fill in some of these, either the reasons or the statements, right? They have you fill that stuff in, so you don't have to generate it completely by yourself. All right, so let's go to the next page. We'll go through this one maybe a little bit quicker. The reflexive property of congruence, I'm not going to talk about him right now. But the symmetric property, if AB is congruent to CD, then CD is congruent to AB. That's kind of like if X equals 2, then 2 equals X. Sometimes you'll see it as 2 equals X, and you'll want to switch it around to X equals 2. And that symmetric property just allows you to do that. The transitive property says that if AB is congruent to CD, and CD is congruent to EF, then AB is congruent to EF. Okay, and then some of you guys might remember the law of syllogism. Syllogism. I know we talked about this in section 4. But the law of syllogism is exactly what the transitive property is. P goes to Q and Q goes to R means that P goes to R. Okay, that's what the transitive property says. So this is just illustrating that also works when we're talking about congruent segments. Okay, so I'm going to go down to example 2. The route for a charity fitness run. Oh, this right here. This is just a proof of the transitive property. So if you want to know, like, I'm not just feeding you a load of crap. The transitive property actually has been proven, and therefore is a theorem. It actually has been proven from some other postulates. So I'm not just feeding you full of crap. The transitive property is legit, and this is why it works. So I'm not going to go through that whole proof, though. Let's go down to example 2. The route for a charity fitness run is shown. Checkpoints X and Z are the midpoints between the starting line and Y, checkpoint Y, and checkpoint Y and the finish line respectively. That word respectively means in order. So X is the midpoint of the start line and checkpoint Y. Z is the midpoint from checkpoint Y and the finish line, right? Respectively means X goes with this set, Z goes with the second set, because that's the order in which they go in, okay? So I'm going to write that down. We stopped here. I'm going to write that down. We're given, I'm just going to abbreviate, and I'm going to shorten some of this. X is midpoint of, I'll call it starting line. I think they label it as S. So I'm going to go SY. X is the midpoint of SY. And Z is midpoint of YF, because it's from Y to the finish line. Z is the middle from Y to the finish line. Okay, so that's stuff that we are given. Okay? All right. Now let's see what else we have. If checkpoint Y is the same distance from checkpoints X and checkpoint Z. So this guy is the same distance from X. So this distance is the same distance from there as it is to here, right? These two are the same lengths, okay? That's another piece of information that I'm given. So I'm going to write that down in my given. And I kind of ran out of room, so I'm going to write it up here. I'm going to write XY is, we'll say, congruent to YZ. We'll do that. Okay, XY is congruent to YZ. That's another piece of information that we are given. Prove that the route from checkpoint Z to the finish line is congruent to checkpoint Y or checkpoint X to the starting line. Okay, so I want to show, this is what I'm trying to prove, is that this guy, is the same length as this guy. All right, so trying to prove that SX is congruent to, is it ZF? ZF. Okay, so let's start writing down stuff that we know. All right, so we have to start with the given, always, always. So I'll try to make this go a little bit faster. I am going to not write down all my given at one shot, which is totally legal. We can totally do that. I'm going to write down X is midpoint of SY, and I'm going to write down Z is midpoint of YF. Okay, so that's given, and I'm not going to write down the other stuff yet, because we'll get to that. Okay, so you don't necessarily have to write all of your given down to start with, but you do need to start with some portion of your given. Okay, so I can separate those out. All right, now what I usually do is if I don't know where to start and I don't know what to do with a proof, I'll write down a piece of the given, and then I'll kind of milk that stuff for all that it's worth. I'll try to gather as much information as I can from this. Until I've completely exhausted everything that I know about that statement, okay? So I know that if X is the midpoint of SY, then if X is the midpoint of SY, if this is exactly in the middle from S to Y, this guy is exactly in the middle from S to Y, I know that this piece right here is the same as this piece right here, right? I know that SX is congruent to XY, right? And I know that because of the definition of midpoint. By definition of midpoint, which was something I think we had in 2.4 maybe, 2.4, definition of midpoint tells me that those two things are the same if X is the midpoint, right? Okay, but in addition to that, I can do the other one, right? If Z is the midpoint of YF, I can say that YZ is congruent to ZF. Okay, and I'm going to do that all under the definition of midpoint. So I'm gonna do that and kind of cheat. I'll put those two steps in one under definition of midpoint. Okay, so I have those things there. Okay, and what I need to try to do is say that ZS, this is what I'm trying to get to. If I'm looking at my proof statement, okay, I'm looking at this guy right here. I want ZX to be equal to ZF. Okay, so SX has to be the same thing as ZF. I want those two things to be the same as each other, right? Okay, now here's the deal though. ZX is equal to xy, and yz is equal to zf, okay? Now xy, if we look at our given information, which we still have to write down, we know that xy is the same thing as yz, okay? So I'm gonna maybe swap that guy out right here and turn this into a yz, right? That way I can say zx is the same thing as yz and yz is the same thing as zf. And then I can do one more thing that turns him back into these two being equal to each other, okay? So let's write down that next piece of given information. So I'm going to go back to my given again, and I'm going to go xy is congruent to yz, and I know that because he's given, right? Okay, now to use that given piece of information, I'm going to do what I just said I was going to do up here, okay? I'm going to change this sx is congruent to, instead of it being xy, I'm going to put yz in that spot, okay? Okay, I'm gonna like basically plop him in there because that's what xy is congruent to, is yz, okay? And then I'm going to leave the second statement alone, so he's going to just not change, but I'm going to tag him along for the ride, okay? So I have this going on now, sx and yz and yz and zf, okay? And how did I know that I could just like take that thing and plop him in there? That is substitution. I just substituted, I just plopped him in. Substitution property, okay? Anytime you're just taking something and plopping him in, he has a substitution property, okay? Now, you might have already figured this out, that if sx is equal to yz and yz is equal to zf, then sx, isn't that equal to zf? This is like the PQQR. This is the transitive property, right? Or the law of syllogism, okay? If something is equal to something and that is equal to something else, then the first part is equal to the third part, okay? So what I can do is I can just jump straight from sx being equal to zf. Sx is congruent to zf. And that's what I was trying to prove. And how did I know that that was true? Because of the transitive property. Okay, transitive property allowed me to do that, and that's the last step of my proof, so that's exciting. I am done, okay? So again, that was a little bit more steps, and it's really hard to generate that by yourself. I'm not going to expect that you guys do that, like your first proof out of the gate. You know, I'm not going to expect that you know how to do that or that you can do that by yourself. But if you followed along with that and was able to see why I justified those steps as they are, then you're doing pretty good at this point. So, you know, we're going to ease our way into this, and it's not going to be too bad. Okay, so there's that. That's all I have for you for notes. The homework assignment, again, is that handout, so make sure that somebody got that and is passing that out to you. And let's go ahead and have you do all of those for tomorrow. I think most of it is fill in the blank. Okay, and we will add these to our note sheet on tomorrow. Okay, or our purple sheet.